When ionic solids form, they form a lattice, which is a three-dimensional arrangement of ions. When sodium chloride forms from its ions, they are arranged in the form of a lattice. Here in this picture, the ion sizes are shrunk to show the connections between the ions, but you see that they create a lattice. When this lattice forms, energy is released. That's called lattice energy. So formation of ionic compound is exothermic. This lattice produces energy because it maximizes attractions between the ions. The stronger the attractions, the larger the lattice energy, and the more stable the ionic compound will be. So the attractive force that the ions attract each other affects lattice energy. If you look at the formula, we got the product of the charges divided by the distance between them squared. Let's see the effect of ion size, or the distance. As the ions get smaller, that means you're dividing by a smaller number, force will be larger, the attraction will be stronger, lattice energy will be larger. Therefore, lithium chloride, having the shortest distance between the center of the ions, will have the highest lattice energy. When it comes to the effect of ion charge, the magnitude of charge on lattice energy, you see that this attractive force is directly proportional to the product of the magnitude of the charges. So you would expect that a larger charge, not the size, but +1, +2, +3, etc., will result in a stronger attraction, therefore larger lattice energy, as you see in the case of, or the comparison between sodium fluoride and calcium oxide. Sodium fluoride is made up of +1, -1 charged ions. Calcium oxide is made up of +2, -2 charged ions. So therefore, lattice energy in calcium oxide would be expected to be larger. And of the two factors, ion charge and distance, the more important one is ion charge. So that's the first thing you're going to look at, ion charge. And then if you don't see a difference between species, you're going to look at size. Let's take a look at this ranking question. We're going to put the given ionic compounds in the order of increasing lattice energy. Remember, lattice energy is proportional to magnitude of the charges and the distance between them. The first thing you need to look at is charges. Magnesium ion is a +2 ion, oxide ion is a -2 ion. Calcium ion is also +2, oxide is -2, and strontium is also +2, being in group 2A, oxide is -2. As you see, the charges are no different. They are the same, which means that we're going to look at size. So how does size change in the periodic table? Look at the sequence of these elements in the periodic table. They're in the same column, and as you go down, size increases. Which means that strontium is the largest, magnesium is the smallest. Well, since we want to put them in the order of increasing lattice energy, the smallest lattice energy will be from the largest of these ions, which is strontium oxide. Then we have calcium oxide. Then we have magnesium oxide. Size comparison. The magnitude of the lattice energy of an ionic compound has observable effects in the physical properties of the substance. Take melting for an example. When you heat an ionic substance, starting as a solid, the energy of the ions will increase as you increase the temperature. At some point, that energy, the kinetic energy of the particles, will overcome the attractive forces between ions that keep them in place as a solid. And the bonds will loosen and the substance will turn into a liquid. The ions will remain as ions, but it will be a liquid. The temperature at which this transition happens is the melting point, where the solid turns into a liquid. The larger the lattice energy, that means the stronger the attraction between the ions, the higher the temperature you need to heat it up to melt it. Therefore, the larger the lattice energy, also the stronger the attractions between ions, the higher the melting point will be. Take a look at the ranking of the lattice energy versus melting points. The larger the lattice energy gets, the higher the melting point gets.